So, good morning, students. This is my second lecture on your digital signal processing. So, in this, we'll be introducing you to the systems. Earlier, we had discussed the signals and we had given introduction on signals. So, this is introduction to the systems. So, starting with general semantic of the systems. So when we go to the general semantics, the first one is that whether it is a continuous time system or a it is actually multiple input or multiple output, or it may be single input single output. Means xt is giving you yt, or it can be x1 x2 up to xm number of, say, group of or a vector of inputs will be giving a vector of outputs. So this is for continuous time. Similarly, for discrete time, you have a similar option, xk giving yk. In some books, it will be xn giving yn. Whether n or k, they are the discrete times instead of the time t. The same thing. So either it is multiple input, multiple output, or single input, single output. Now there are some multiple input, single output, and single input, multiple output systems also, which are not very uh, being discussed here. But once you are discussing multiple input, multiple output, everything is put into that together. Now, going to the different examples of the systems, the whether if it is a electrical circuit is one type of a system, where you have voltage source, current flowing, you have inductor, capacitor, and so on. And similarly, if it is a semiconductor, diode also is another system where you have input current, and based on that the current changes in the output. In the case of the electric circuit, you know that you give voltage in one form, and across capacitor it is coming in a different form, across a resistor in a different form. So IR, IL, IC are different. Similarly, in amplitude modulator, you put a modulating signal like our AM, or where we have a particular offset for modulation and a carrier wave which is modulating the signal. Those who are from the communication background, they know that very well, or at least basic communication most of you circuit background students have studied. So whether it is amplitude modulator, or for mechanical water pump, where you are having the input water and this is regulated based on the height of the water, it is regulated and so on. So this is another type of system. They are following different equations and different kind of outputs. Delta modulation is a digital kind of modulation where you have input signal and digitally giving zeros and ones in a particular way. It again follows another set of equation, and delta modulation is done by another digital system. So it is an analog system, this is a digital system, or this is a mechanical system, this is a electronic system, that is a electrical system, or what is the most common thing of your digital signal processing is the digital filter. So there's a name suggests digital signal processing. So you have to digitally process a signal. So for that you need a digital filter. Just like uh, in analog we need analog filter, in digital we need digital filter. So digital filter is what you'll be having one type of waveform in the input, and you'll filter that, and you give another part of waveform in the output. So now to classify the systems, there are actually basically 6 different basic categories. Before that, I'll just show you the systems. One, it may be a continuous time system like we had given the equation earlier, or a discrete time system. So the 6 basic categories which I'll be discussing in this class today are: number one, linear and non-linear; time invariant and time variant, or time varying signals, means signals that change with respect to time and signals that do not change with respect to time; systems with or without memory, or sometimes it is called a static or dynamic systems also; then causal and non-causal systems; then invertible and non-invertible systems; and the last one, stable and unstable systems. So let's discuss on these 6 one by one. First, linear and non-linear system. So here what we have is a continuous time signal. If system is there where this system, when it gets input x1 gives output y1, and when it gets input x2 it gives output y2. It is something like when it is 1 ampere I get 1 volt, when it is 2 ampere I get 2 volt in the output, kind of thing. Now this is linear if it satisfies the additive or homogeneity property. Means the additive property is that when we have, instead of 1 volt, we have 1 ampere; for 2 volt we have 2 ampere. So when I give 3 volt, which is a combination of 1 plus 2, I get 1 ampere plus, say, 2 ampere. So This, if these two are satisfied and if the third already is being satisfied, then it is following the additive property, and it is but not exactly linear unless it does have homogeneity property. Homogeneity means when I have 1 volt and I get 1 ampere, so when I have a multiplying factor 2, alpha equal to 2, so then 2 into 1 volt, that is 2 volt, I get 2 into 1 ampere, that is 2 ampere. So if both are satisfied, then it is a linear system. So irrespective of this alpha value, if these things are followed, both the equations, then we consider these two properties together to be the principle of superposition. Superposition means if I have two voltage source for getting correct, so individually those two voltage source will be giving two different individual. Say for example, voltage source V1 is giving current I1, V2 is giving I2. So when I add both the voltage sources V1 and V2 in the system, I get current I, which is equal to I1 plus I2, means combination of these two. So if this kind of situation is prevailing, then we say the system follows the superposition theorem or the principle of superposition, and if it follows the principle of superposition, then it is a linear system. Now this kind of systems you have seen, those who are from circuit background, you have done basic electronics or basic electrical, where you have resistor based circuits which are this kind of linear system. But once you have a capacitor or inductor in the picture, the scene is not the same, so it becomes a non-linear circuit. So those circuits which do not follow this superposition are non-linear systems. So anything that is not linear is non-linear. So for linear, alpha, the homogeneity property thing, and there say b instead of alpha you have another term that is beta, arbitrary numbers. Alpha into x1, beta into x2 gives alpha into y1 and beta into y2, whether it is t or whether it is k for discrete time system. So anything that is not, if a system, if a linear, if a system is not a linear discrete time system or not a linear continuous time system, then obviously it is a non-linear continuous time system or a non-linear discrete time system. So I hope this linear and non-linear part is clear. So if you uh, are clear with this, next let's go to the next or the second type, which is time varying and time invariant system. As the name suggests, time varying means uh, any system that changes with respect to time, and time invariant means the system that doesn't change with respect to time. It is something like, say, one person till so we have seen this kind of time varying and time invariant people around, so you can correlate this to them. Say for example, today you are in power, so everybody will love you, and tomorrow you are not in power, so everybody doesn't love you or doesn't acknowledge your thing. So these kind of people who do not love you when you are not in power are time varying system. And the people who love you irrespective of, like your mother and father, who love you irrespective of whether you are power, you have money or not, so they are time invariant system. So just this is a simple way in which I tell my students so that they can correlate what are these things. So coming to system 1 yt sine xt, and system 2 yt t sine yt. The first one, system 1, you see here the yt is equal to sine xt, and system 2, these are, this second one is time varying because here time is a multiplying factor, whereas here the first one is a constant, and this k coming here is making, so these are the discrete time system. In discrete time, system 1 is time invariant and system 2 is time variant, and in continuous time, system 1 is time invariant and system 2 is time variant. So in continuous time xt yt is time invariant if x t minus t0 gives yt minus t0, means if you have a delay or a fundamental delay time of t0, it or time shift of t0, that same time shifts comes in the output also. Similarly, for discrete time, xk and giving yk will give xk minus k0 giving yk minus k0, where k0 is the time shift or discrete time shift you can consider. So the other systems which do not follow this formula, obviously, or they can change with respect to time, are time variant systems. The third is system with memory and without memory, or in short, they are called static and dynamic systems. So the ones which are with memory are dynamic systems, and the systems without memory are static systems. Static means it doesn't change, and dynamic means it changes. It changes if it has memory. It doesn't change if it doesn't have memory. So a continuous time system is said to be without memory or memoryless or instantaneous, or you can say static, if its output yt at time t equal to t0 depends on the values applied for xt for t equal to t0. So here you have only here resistors. We don't have inductor or capacitor which stores charge. So this kind of system is without memory. The systems where capacitor or inductors play their part means they store some charge or store some energy. They are said to be with memory. For digital circuits, the same thing happens. Only difference is that instead of inductor or capacitor storing the energy, you have D flip-flops or T flip-flops or memory slots which are storing a bit 0 or bit 1, some kind of thing. So in the other hand, if you have inductor or capacitor system, so it is called a dynamic system or a system with memory, as it stores some energy, and it is not the same whether it is this time or that time. So likewise, a discrete time system is said to be memoryless if its output yk at instant k equal to k0 depends only on the value of input xk at the same instant k equal to k0. Now, if it changes, it is dynamic, means it changes with respect to time, or it is a time varying system. And normally time varying systems, maybe most of them are with memory, and the static systems are without memory. Otherwise, they are said to have memory. Next, coming to the fourth one, causal and non-causal. So what do you mean by this causality? So a continuous time system is said to be causal if its output at time t0 depends only on the input xt for t less than t0. Means it doesn't depend on the past or future outputs. Means present time is the one which is helping to calculate the thing. Similarly, a discrete time system is said to be causal if output at time k0 depends only on the input xk, where k is less than k0. Both the same things, only difference discrete time and continuous time. So a system that violates this causality is called non-causal or anticipative system. Anticipative system means anything that can predict the future is a non-causal system, or it can anticipate what will be the output. And any system which cannot predict the future is called a causal system. Means we normally, all practical systems are causal, because any practical system cannot give you a output which will come in the future. So all memory systems are causal systems because the output at any time depends only on the input of that instant. It is not dependent on the memory value, or you can say the dynamic systems are non-causal. So systems with memory can either be causal or non-causal. Causality is required condition for system to be physically realizable. Why? Because if it is not causal, means it is able to calculate some future values. Now, if it is able to calculate some future values, then the system is not realistic, because how can you realize a system that physically which can predict the future? So you cannot get future outputs without knowing the situation. So normal all systems that can be made in hardware or circuit is causal. It will be based on present input and past input. Past input we can store it, and present input you are getting it now. So if it is a continuous time delay system like yt equal to x t minus t0, so it is, there is a time delay. It is having memory, but it is a causal system. But if it is a time forward system t plus 2, it depends on advance output or the outputs which you are yet to get, then it is a non-causal system. Similarly, for time delay it is a causal system, and where we have time advance it is a non-causal system. And if it is a linear system where you have x minus 2 and k minus 2 and k plus 10, because of this plus kind of situation we have outputs which we are, or inputs which will come in future, or we have to predict those, or anticipative, so it is non-causal. Next, coming to invertible and non-invertible system. Now, what do you mean invertible? Means the one which can be inverted, or it can be uniquely determined. So a continuous time system is invertible if the input xt can be uniquely determined from the output yt produced in response xt for all time t belongs to minus infinity to plus infinity. Invertible means we can produce a system which can replicate this. Means I can create a copy. Like China is very good in copying. Say you have a new release of Apple iPhone, and it will copy the Apple iPhone's chip. What it will do? It will take the chip, see its input and output, give all possible inputs to that, and see all possible outputs you are getting. Based on the combination of I/O that they get, or all possible input and output they get, they make a chip which behaves in the same way. They do not know what is inside the chip because Apple has protected it, or maybe has made a circuit which is very tough to crack or something. But if you know the input output pattern, you can uniquely realizable. So any system which can be uniquely realizable, it is invertible. So a discrete time system is called invertible if given arbitrary output yk of the system for k belongs to minus infinity to plus infinity, the corresponding input signal xk can be uniquely defined. Now why we are saying we uniquely define? Because if I get 30 and somebody else also get 30 for this same question paper, if two people get 30, you cannot discriminate who's the first and who is the second or who is the best. But if there is only one person who is getting the highest marks, then you can consider him or her to be best. So to be invertible, two different inputs cannot produce the same output. So if two different inputs or two different people get the highest marks, then it is not invertible, or you can say that they are not both the first people. So in such cases, the input signal cannot be uniquely determined from the output signal, because here there is no discrimination whether input 1 has come or input 2 has come. In both cases, you get output y. So a direct consequence of invertibility property is the determination of a second system that restores the original input. So if you are able, if a system is invertible, then there will be a unique output for a unique input. So any system that is giving a unique output for a unique input, that system is invertible. And the system that is not invertible, it will not give unique uh, output for unique input. So a system is said to be invertible if the input to the system can be recovered by applying the output of the original system to the second system. The block diagram we can make here is that, say, system S1 is giving output, say we have X1 giving output Y1 for system S1. So with output Y1, if we can get back X1 dash, which is same as X1, then it is an invertible system. So the second system which produces the inverse or x1 dash is the inverse of the original system. So this is the continuous version, this is the discrete version. So xt coming in the continuous time system giving yt. If it is invertible, you can get an inverse system and get back xt. Similarly, xk giving discrete time system is giving output yk. And if it is invertible, you get an inverse system and you get back xk. And the systems for which you cannot get an inverse system is obviously a non-invertible system. Now coming to the last one is stable and unstable systems. So stable and unstable systems mainly we define based on bounded property of the signal. Stable means you have a stable output. Unstable means you have an unstable output, or output reaches infinity, or there is something like a short circuit or something like that. So normally in electrical circuit we say that array circuit jal gaya hai, or something like that. So here what we'll do is unstable systems are the systems which where like your system becomes hang. We say array computer hang ho gaya. So that computer being hang is actually is that some instability has come there, or a continuously there the system is in a loop or something. So this kind of infinite loops and those things should not occur. So we have to define the bounding property of the signal. So a continuous time signal xt or a discrete time signal xk is said to be bounded in magnitude if xt is having a value bx which is less than infinity, and for any time minus infinity to plus infinity, xk is lying between infinity to xk. So this xt or xk has to be a finite number bx which is greater than equal to that. So we have to know this bx. If the bx is a particular value, then we know it is a finite system. Stability criteria for the continuous time and discrete time systems is that a system is referred to as bounded, having bounded input and bounded output, and is stable if an arbitrary bounded input signal always produces a bounded output. So stability criteria is met means if you have a bounded input like bx and you have a bounded output like by, so x has to be less than bx and y has to be less than by. So if you have a finite value, instead of being infinity being the largest value, if you can define a largest value for the input and a largest value for the output, you consider it to be bounded input and bounded output. So a system that produces bounded output for a bounded input is called BIBO, bounded input bounded output stable. And if it doesn't produce that, it is an unstable system, because either the input is unstable, output is unstable, or both are unstable. So in other words, if an input signal xt for continuous time signals or xk for discrete time signals satisfy the above equation, then it is applied to ct or dt, it can produce bounded output by, and here by xk less than by, then it's called a stable system or unstable system. Now, as we know about the six types of systems we have already discussed, now these six types of systems can be connected in three different ways. So for interconnection of different systems, we can generate complex structure based on small systems. So here, if you are asked to design a particular system, it may be a very big system. So what we do is that we break it down to small systems, and individually we generate the small systems and then interconnect them to make the big system. So we handle small things, and together the small operations make the major operation. So in signal processing, complex structures are formed by interconnecting simple linear and time invariant system, which is in short called LTI systems. Linear and time invariant means LTI. So we connect different LTI systems and produce a big system. So here we describe three widely used configurations. More combinations are there, but these are the most three popular one. The first one is cascaded, means one after the other. Second one is parallel, one parallel to the other. You know about that. And the last one is the feedback, means where the output is being fed back to the input, and based on that you are refining the output. So first, coming to the cascaded configuration, here what you have a series connection, or those circuit background people know series and parallel. So series connection means one after the other the systems are connected in series. So you have the first system S1, uh, the input of S1 is giving a output of S1, the output of S1 is becoming input of S2 and giving this. So this is how XT giving WT, and this WT is input to S2 and you get Y2 YT. If the interconnection of the system S1 and S2 are linear, it is straightforward to show overall cascaded system is linear. Likewise, if two systems S1 and S2 are time invariant, then overall cascaded system is also time invariant. Means if S1 and S2 both are LTI, then the whole thing is LTI. If S1 and S2 both are linear, the whole thing is linear. If S1 and S2 are both are time invariant, both are time invariant. Another feature of the cascaded configuration is that the order of S1 and S2 can be interchanged without changing the overall response. XT giving WT giving output YT. So what you can do is, if you instead of S1 and S2, you make it S2 and S1. Say for example, we are having a system S1 giving output S2 like this. So here we have XT giving here YT. These two are fixed. Here we have WT. Now if I change it and make S2 S1, here the same input is there, but here instead of WT it will be VT, and output is again YT. Okay, So here S2 is coming first, you get VT. S1 is coming first, you get WT. But input and output is remaining same because it is linear and time invariant. Okay. So like this, we can have this kind of thing. Next, we can go for the next one, the parallel combination. So parallel configuration means here the parallel configuration as in the figure here is S1 and S2 is here, and we get output Y1 and Y2 and giving output YT. So they are in parallel. So overall output is determined by the output of the individual system, or other words, if X1 generates Y1, X generates X2 generates Y2, and together X generates Y1 plus Y2 when this S is in parallel. So as for series combination, the system formed by parallel combination of two systems is also linear. So if S1 and S2 are linear and time invariant, say we are having this is LTI and this is LTI, then the whole system is LTI. Okay. So if they are time invariant, the same thing happens. So both, if linear and time invariant is there, so both are LTI. The feedback system is very common. The feedback configuration, as in the figure, the output S1 is fed back to the S2 and then subtracted from the input signal. So you have this XT. So this XT is going here, and whatever it's going here, it's going back here along with the. So these two are coming there, and based on that, you are making a change. So it is subtracted from the original signal. So X is X minus W is generating here. So this is the feedback system. So such systems are very difficult to analyze at present, but what we'll do, we'll use Laplace, where we have XS, or we have Fourier, we have X omega, or we have Z, where we have XZ. So these, what they do, they transfer time domain to frequency domain. Okay. So here all these are frequency domain thing: Laplace, Fourier, Z, transform. So when we'll be discussing that, then this thing becomes easier. So thank you for your patience. I'm ending here, and stay tuned for the next lecture.